Morning, everybody, and welcome to Astronomy 100. Today is Tuesday, August 24th, and we have quite a few things to look at today. We have a few discussion prompts. I think there are 3 of them. And I know we are in the beginning, and I'm talking about the number and so on and so forth. Down the road, probably we will not know how many, so we will basically just as we go along, we discover some along the way, okay? So the purpose of today actually is to introduce you to week 2 model and see how that is structured, because it started to look more and more the shape of how each model would look like, because there are a couple of items that I need to bring your attention to that you didn't see in week 1, and that is because you cannot see them in week 1 since they relate to the prior week. Since week 1 did not have a week before it, so we cannot really include those items until week 2, which is today. So we're going to go through those additions, and this is basically most of how the model would look like. There will be a couple of items extra. There will be popping up once in a while, and they have to do with the quizzes, and they also have to do with the homework assignments. So those are the things that you need to be watching for. Other than that, the model itself is really what it looks like for the rest of the semester. So this is basic, okay? So I hope that you guys have had the chance to go through them and also see the changes, and we're going to talk about that one. Before I do that though, let me dive in directly into the first prompt of the day, the first item that I need you to answer to today. And that has to do with last week's discussion related to the syllabus. So let me share the screen with you. First of all, let me switch to student view. And let me share with you the screen to tell you exactly what I'm talking about in here, so that we have an understanding of what needs to be done. Okay, are you guys looking where it says ASTR 100-09? At least I need one person to confirm.
Yes.
Very good, thank you, Jordan. Okay, and Kova. Okay, so this is basically what I was talking in terms of how the models would look like most of the times. There might be an activity in here, like in here. Okay, this is an activity actually. And there will be a terminology. Those are the words basically used in this chapter so that you will have like a summary of the concepts. And in here, there is a review of the previous chapter. So this is what I was talking about, that this cannot happen unless we have had a week at least ahead of time. In this one, if you go through it, you will see, let me see if I can open it. Okay. Okay. Yeah, because I'm using a non-existing student called the test student, so I cannot see these things, okay? So it's asking me to sign in because this account is not a real account. Anyway, for you, when you click in here as a student, of course, you have to go in order, and it's just to view things, and it's not really as the first week where it was the sequencing thing. There will be at times, for especially when we have assignments, where the assignment is connected to the previous discussion or item. So when you go in here, you will find 3 little over 10 minutes, about 10 minutes, 2 of them 10 minutes, 1 of them is 12 minutes, videos. Each and every one of them is connected to these units. What I want you not to do is to assume that somehow this replaces the reading of these units. Even these units in here are just basically a PowerPoint, a summary of that unit. It's still your responsibility is to read the entire unit, okay? Because that's where you're going to be tested on. Not on the summary, not on my interpretation of the unit, because they may be focused on an item in the presentation, whereas there are other items in there that are assumed to be connected to our previous concepts, or concepts that you should know, or concepts that are probably not, at least I did not bring up in the discussion here. When it comes to test time and exam time, the entire unit is going to be included. So that is not a replacement of the reading assignments. So this, if you open the book, you will see unit 1, followed by 2, followed by 3, and that's what you should have had done in here by now, okay? So we're going to come back into this structure again, but let me delve into the item of the discussion today, the first item of the discussion today. If you click on the syllabus, as we talked about last time, and you go down into where the textbooks and other resources, this is the book. The 6th edition, by the way, will do. I didn't see any difference so far. I have both of them, and if I notice something, I will let you know, guys, if there is any difference. So this is textbook, but what I'm going to talk about today is this link, stellarium.org. Here is where the prompt is, okay? I need to know where you stand on this software. That's all. So that's prompt 1. So let me click on the link, and then once it opens, let me stop sharing first. Once it opens, I'm going to share with you how it looks like, again, just to make sure that we are on the same page. It's not this page. This one? Yes, it is. So that we are on the same page and we have the same understanding. Where was this one? Share. And it's this. Okay. Again, this we saw it last time. And chances are you either have downloaded the Mac version or you have downloaded the Windows version, okay? These are free, like you don't have to pay anything for them, including this ones, by the way, the Linux, if you happen to have a Linux machine. So this is 100% free. You don't have to worry about paying for anything, okay? So I assume that you have done that part and at least your way through it, okay? Now, if in case that doesn't work, if in case this does not work, then you can use the web version. The web version is similar to this one's. I heard from one of you guys already that the web version probably does not have the shortcuts, namely, for example, L to speed up the video, to change the time rate. And if you're running into that situation, you should be able to control it with the mouse. So the shortcuts can still be run with the mouse. There is the instructions in here. That's a text, basically instructions. Here is, again, the prompt of the day. I need to know where you stand. Either you tell me I am 100% ready, I already downloaded the desktop version and it's working fine for me and I'm ready to go. Or you say, I could not have downloaded the desktop version because the computer is not mine, it's a loaner or something from the college, for example. And there is restrictions, they cannot install stuff, therefore I'm going to use the web version. In either case, I think that you should be ready. Now, if you cannot, for some reason, you had difficulty with the installer, or you had difficulty with the web, for example, I don't know, I don't know what it could be, like the computer, for example, I doubt that doesn't have internet, or you don't have internet access where you are, for example, in a remote area, and you probably have to come to campus to make that arrangement. We have to talk about that situation in case you have issues. I need to know. But the point is, I need to know in the discussion that you have gone through these steps and you are ready, okay? If you are not, I really need to know that, okay? So that is item 1 of the prompt today, is to tell me where you stand in terms of that software. Makes sense? I'm sorry, I did not hear that. Can you repeat what you said? Okay, very much. Very good. That's very good. Okay, so basically that is what I want to know. I want to know to make sure that we are on the same page. Because, let me go back into the, where it was, share syllabus again page. If I go back into the modules again, this week's model, we have this activity. This is a freebie. You're not going to be graded on this one. So you can mess it up if you like, as much as you like, okay? You can really, I mean, if things don't work out, you can always restart the program. This uses Stellarium, okay? This uses Stellarium. So if for some reason, for example, it tells you to hit the letter C and then followed by the letter K and then followed by the letter L or whatever, and then L, you have to hit it so many times, like 5 or 6, even 7 times, and you notice that this thing starts to spin too fast and you cannot control it, then just restart the program, kill it and restart it again, okay? Or if it's a web page, refresh the page, okay? Hit F5 on it or close it and open it again. So basically, the purpose of this one is twofold, 2 things. First of all, to get to know Stellarium up close. You really will have to know it very close. And then you will see when I discuss items 4 and 5, that the discussions of the zodiac signs and also the constellations are actually connected to these units. Okay, so it has 2 important applications. The first one is the fact that you discover the zodiac signs and the constellations and the motion of the sun, the apparent motion of the sun in the sky and so, things like that, and the ecliptic and all of these concepts that are talked about in these units. When you do the activity, it comes alive to you and you will see it before your eyes. That is one thing. And the other thing also to get to know the software more and more, because we're going to need it down the road, where it's going to be graded, where it's going to hurt if we don't do it right. So are we clear on the first prompt?
I am.
Very good. Very good. So, very good. Glad to hear that. I know I'm reacting to the chat also, okay? So, let's talk into about this units in here and see. This is terminology. This you will see it from now on. Every time you will see a page like this one, it's basically the words and more in depth, and it's actually enrichment. These are the zodiac signs I was talking about in here. This is really called the, it's not a real zodiac sign because there are only 12 of them, but this is actually also a constellation that the sun goes through because there are only 12 signs of the zodiac, and this is the 13th of Ophiuchus. This is an extra one. It's called the 13th sign of the zodiac. But the point being in here is this is how the sun looks if we are sitting on the earth, looks like it's going around. Okay, of course, this we cannot see it. This is what we will see during that night because the sun is. Yes.
There's 12 zodiac. I mean, there's 13 zodiacs and only 12 are observed. Why is that?
That's because there are usually people agree that there are 12 in the sign, 12 signs, because the 12 month, basically 12 regions, if you wish. But if you look into between the Scorpion and the Sagittarius, there is a space where it goes through this one. Okay, so that they did not include initially, and it's not included except later on because the sun actually goes through that constellation also. Okay.
So since we only created a 12-month calendar, they decided that they just threw that one out.
Yeah. So it skips in here.
Horoscopes are messed up then, right?
Yeah, of course, astrology is not a real science, so we have to be careful.
But seriously, that just was like, whoa, I was like, okay, thank you for answering though. I know it's not real, but that's just kind of mind-boggling that just because we created, there's 13, but there's only 12. I'm new. I'm learning that. That's crazy. I just went my whole life not knowing that.
problem. The thing with it is, this is a summer sky, the summer nights. Of course, you can see June and August. Scorpion, of course, is really a big constellation during the summer nights, where you can pinpoint your location based on it. You can really basically orient yourself based on it, and you can find all kinds of interesting things. So during the summer, this is what you're going to be looking at. We're in August right now, and then as we move along, this is basically how the Earth is moving, and we see these constellations as the Earth. Unless we have a solar eclipse, we cannot see the other constellations in summer. We see them in the winter, though, when we are on this side. Okay, and that's exactly the whole activity that you're going to be doing in this one. I encourage you to do the readings. By the way, this is a tabbed activity, meaning that if you click on another tab, it's going to give you other information in here. Among other things, it's giving you a lot of information. By the way, this link in here, the retrograde motion of which one is this one? It's in general. Okay, so we can do this one for Mars. And when you do this activity, by the way, the one that is toward the end, and if you pay attention to the planets Venus and Mercury and even Mars, you will see that actually they move around back and forth, okay? They will exhibit retrograde, because at some point it asks you to accelerate the rate. It's not moving at the rate of 1 second per second. It's moving at the rate of several days, several months, sometimes per second. So you'll see several months span in front of you. So you will exaggerate the retrograde motion, okay? So, and you will see it actually in the activity itself too. So there are a lot of benefits from that activity. There are a few questions at the end. Again, it's not an graded activity. So you really, I hope that you will enjoy yourself. You will really have fun doing this, and think of it as a game, basically, where you're doing things on the computer, trying to learn these things. By the way, it's very hard to do this on the planetarium on campus, to do some sort of an activity. Even if we have the access to a planetarium, I will still ask you to do this one on computer, because computers, you can do all kinds of things. I mean, there is an animation I have developed last year, and actually I can share it with you, where I brought so many planets together near Jupiter. I brought the Neptune, Uranus, and Pluto. No, what am I talking about? Saturn, Uranus, and Neptune closer to Jupiter, and I also brought hypothetical planet 9 closer to Jupiter, and you will see them basically collide with it. You cannot do this something with like this one with the planetarium. You only can do it on a computer. You can do whatever you want to on a computer. You can simulate stuff, but this is not a simulation. By the way, that the thing that you're going to be doing toward the end, you're going to do actually a real observation, except that the time is accelerated. The time is moving at a higher rate. Instead of waiting for 5 years to do the observation and collect the data, you're going to do it in about 20 minutes, okay? And you will be done with it. So that's the advantage of doing these things. Again, so I hope that you do the reading, and in here, the astrology, the point that we were talking about, the constellations, and in here, you can clearly see the Scorpion and Sagittarius, and there is no constellation in between them, okay? There are what? 4, 8, and 12 constellations, but the 13th one is not mentioned in here. So if you're interested, at least into educating yourself about what people talk about when they talk about astrology, it's not real science, it's a pseudoscience, okay? Because if everybody is born, for example, in Cancer, is supposed to have that prediction that the astrologist makes, how come there are different, basically, careers and different people with different, basically, how should I say, luck, if you wish, based on that constellation, okay? It's not your birth that determines what happened to you. Anyway, the point in here, and modern astronomy, this is a little bit of background. We're going to get into more details onto these concepts, but let me go back into where we came from, if I can go back. Yeah, this is basically, I told you I cannot access this one because I'm not a, this account is not a real student, it's just a test student. Then we're going to get into the units in here. For that, let me open them, first of all, if I can. Somebody saying something in here?
No.
Yeah. Okay, so Because sometimes when I'm talking and I hear something that I might need to be quiet too. Okay, hold on. Let me grab the information I need first. So as we talk about units 4 and 5 and 6, what is coming. And as I was saying in here, these are not a replacement to, I am still sharing the screen, am I not? Yeah, I think I am. This
Yeah,
shows.
yeah,
Very good. Very good, thank you. So the units in here, you are supposed to do the readings for them. You're not going to rely on the summary in here. You're not going to rely on my description of those summaries, okay? You're going to really do the readings in here because that's how you're going to be graded. When it comes to quiz times and exam times, you're going to be graded on this one. So this is really the bulk of the stuff. If you have questions about it, or if there is an issue with it, please let me know. And that is very, very important that we have to get all of this materials through. Then this week, we have the new units. So let me talk about this 3 units, and you will see the connection with the activity right away. So you're not going to even basically wait for me to tell you that. Let me go in here and let me share with you unit 4. Okay. For unit 4, it delves with two points in here that have to do with the scientific method. A scientific method is like prescription, step by step on how to do things, okay? Start with an observation, you make a hypothesis, you test the hypothesis. Based on the test of the hypothesis, you could really, if the hypothesis is proven wrong, then you can go and make up another hypothesis. And if it's correct, then you try to build a new experiment and see if it still holds true. And you build knowledge basically based on that way, and you move on. So in other words, there is a testable step-by-step process through which you can go. 2 words of caution here. First of all, sometimes it's not in the same order as the prescription says to, basically. Again, scientific discovery sometimes can happen backward. And that's fine, as long as you can subjugate that discovery into the same rigor and the same basically method, so that it still holds true, then it's good, okay? It's like, for example, you're trying to do your best breakfast, and sometimes it calls for step 4, for example, put salt, step 5, put half a teaspoon, for example, of black pepper, okay? But what if you switch the 2 orders backward? Sometimes it doesn't hurt, okay? You put the black pepper and then you put the salt later. So that is more or less similar, if you wish. I'm trying to put an analogy in here. The scientific method sometimes can happen in a not the same order, not the same basically how the prescription says in here. In the book, it gives you like a big circle, basically a process, a cyclic process through which you go through. Okay. Here is the deal. Once a law is discovered, once the law is formulated, I should say, based on observation, it needs to be tested. And it is going to be true all the time, unless a test proves it wrong. Doesn't matter which test. So if you could have had successfully tested it 1,000,000 times, and all of them is a check, 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 pass, 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 and one test fails, after the 1,000,000th test, the whole thing has to be abandoned. It's no good no more. Doesn't matter. The ratio of 1,000,000 to 1 doesn't matter. 1,000,000,000 to 1, it doesn't matter. It fails once, it's no good. Then we have to come up with a new hypothesis and see if we can test that one. And the new one becomes a law, if it's true, of course. So that is more or less the approach. And you're going to see it in hand in here. You're going to see it actually in astronomy is the best field for that. You will see the scientific method. We came up with a hypothesis. For example, we said, okay, the Earth is the center of the universe because if we look into the sky, everything seems to be revolving around the Earth. And they seem to be going in perfect circles. And I just mentioned the retrograde motion of Mars, for example, which was an obvious case people could observe. So we needed to explain this one. So Ptolemy postulated the following. He said that, okay, yes, everybody is going in a circle, except when it comes to Mars, it's going in its own circle around the big circle. The reason why they really wanted the circles is because the heavens are perfect, therefore circles are the best shape. And that is why the idea was there. So as Mars is going around the Earth in a circle, at some point it appears going backward because it's going back in its own circle. So that was a good hypothesis. Except that there was a problem with the calculations with this one. So in order to, because it did not really fit exactly for how long it's going to go back, it fits sometimes it doesn't fit. So he said, okay, wait a minute. At least the people who came after him said, wait a minute. Mars is actually going in a circle around the circle, and that circle is going on a big circle. The model starts to become complicated. Later on, Venus also happened to have the same retrograde motion, people discovered, and the model started to crumble. So you see how the hypothesis was just to explain something that we observed, and the model started to come apart. It took Copernicus to look at it and say, you know what? It's not actually that everybody is revolving around the Earth, but everybody is revolving around the sun. And that all of a sudden made sense for the retrograde motion. Retrograde motion now started to put better because now, as the Earth is going faster than Mars, sometimes Mars is in front of us and appears to be moving forward, but as we catch up with it, it appears to be going backward, as if you're driving on the freeway and the car in front of you is moving and you can see it moving forward, but as you catch up to it and you look at it and it looks like the car is moving backward, and that's because of the relative motion. The same thing is actually happening with Venus and the Earth. Venus is actually moving faster, so it catches up to the Earth, and sometimes it appears to be moving backward, and sometimes it appears moving forward because of that relative motion. So that made sense perfectly. It started to pick up stuff in here. But people started to question, I mean, why do we have to believe you, Copernicus? He came up with an explanation that somebody explained, and we can put more and more circles as we want to go to. I mean, we know that model is not good and complicated, but we'd still explain things. Then Mr. Galileo looked at Jupiter and saw that indeed, because they still wanted the Earth to be the center of the universe, okay? We are humans and we are it. So we are really the main thing in this universe. So everybody has to revolve around us. So that's why they didn't believe Copernicus when he came up with that. A lot of people did not because of that. It took, again, another astronomer to later on say, wait a minute, it's not just the, there are actually other objects that revolve around the other objects. So the Earth is not really the center of everything. Like, for example, Jupiter has, when Galileo looked at it, has 4 moons. The first night he saw 3 moons, the next night he saw the 4th moon. And here is Io, Europa, Ganymede, and Callisto, which are the 4 moons, revolve around Jupiter. So the idea that everything revolves around the Earth is not true anymore. So there were a lot of things in here that come up with these things in here. And then Mr. Newton came up with this beautiful theory to explain all of these things. So that's nearly a theory now based on the law of F equals to ma, based on physics, based on the law of gravity and all of that. That explains everything. And everybody was good. Everybody was happy. There was only a nagging issue that nobody could really deal with, and that is with the orbit of Mercury. The orbit of Mercury was odd. Everybody is revolving around on the same plane called the ecliptic plane, except Mercury, sometimes its orbit leaves that ecliptic plane and comes back to it. And it's precession that we couldn't calculate based on Newton's model. And that was a problem. So we really had to abandon Newton's model. We really had to abandon the law of gravity and Newton's laws. Mr. Einstein came up with a better theory that explains everything, including everything else before, and including Mercury too. So that's where we stand on things. So do you see how the ideas evolve, and the hypothesis and the scientific method is that? If you take the scientific method and test whether the hypothesis of the flat Earth hypothesis, you will see that doesn't hold water at all. All kinds of observations that don't fit the picture of the flat Earth. Same thing with astrology. If anything at all you can take from this class is the scientific method. You're going to take it and test with it ideas like this one. So if somebody stands before you and start talking nonsense, then you can hold them based on the how it was tested. What's the accuracy? And then the counter argument to it based on science. That is really, it's an important unit. Okay. We're going to discover this one in practice. We're going to see it, how it works firsthand. Okay. And then describe the characteristic of the atomic model. And here we're going to, when you look at the book, you will see that the atomic matter, in addition to the atomic number and the atomic mass concepts that we will see a little bit more down the road, there are some relevant astronomical data for the elements, how abundant they are in the universe and how they were formed. Okay. And the fundamental forces and the elementary particles. Of course, the elementary particles that we know today are protons, electrons, and neutrons, but those are not really the elementary particles. There are some, because the proton and the neutrons, they are made up of tiny particles called quarks. So we're not going to get into all of these details, but the point being is the four forces. There are four forces in nature. That's it. In terms of strength, from the weak to strong, or I should call it from the super weak to the strong, the super weak of them all is the force of gravity that holds the entire universe, the galaxies, the planets, us together to the planet, is the force of gravity. Followed in strength by the so-called weak nuclear force. The weak nuclear force is the one responsible for radioactivity, which is a big deal. Okay? Without it, the Earth would not maintain its magnetic field. Hence, there will be no life on Earth. Then followed by the force of electricity and magnetism, the one with which you can see, the one with which you can touch, the one with which you can smell, the one with which you can hear, the one with which you can sit on something and basically interact with it. Because if you sit, because of the electrostatic force that is preventing your electrons and the electrons of the chair from touching one another, that's why you can sit, otherwise you're going to go through that. You can, the light, the computers, the phones use electricity and magnetism, which is a very important one. And then the strongest of them all is, of course, the nuclear force. And the nuclear force, strong nuclear force, that is what holds the proton together, the neutron together, and what holds the nucleus together. And without it, of course, there could be no proton, no neutron, no matter as we know it whatsoever. We will not be here talking about it. So those are the four forces in nature. Later on, at some point, we're going to talk about the evolution of the universe when we talk about cosmology, and we will see how these forces can explain and interpret the Big Bang. Okay, it's important, this concept in here. And how mass interact, that's the force of gravity, charges interact with electricity. I'm talking a little bit more what the book is talking about in here. I know that, but I'm doing it on purpose. You still are responsible for doing this unit and reading it. So let me find where unit 5 is. Okay. Let me stop sharing. Let me share with you unit 5. Share unit 5. Okay. Again, in here, it's going to talk about the celestial sphere. When you look outside, it looks like it's a dome. All the objects, the stars, the planets, the moon, everything assumes like on one big dome. If you look at it from the east, the horizon, where basically the sky and the ground meet, that is the east. You go 90 degrees, that is north. You go 90 degrees, that is west. You go 90 degrees, that is south, and you go 90 degrees back again, you're where you started from. So 360 degrees or 4 times 90 degrees will take you back to where you started from in the horizon. And you can do that actually everywhere, okay, in the night sky. If you look at the north, for example, doesn't matter where you look, by the way, the north is a good example to start with. And then you move up 90 degrees, that's the zenith, that's immediately above your eye, above your head, okay? If you go back 90 degrees, you go back into the horizon again, behind you in the south. That is because we started from the north. This is a half dome. This is a dome, basically, a half like sphere. This is where everything, this is called the celestial sphere, where everything can be pinpointed using the angles, depending on which direction you start from the east, and depending from the north, which angle you would want to go to. So every object is located on the night sky that way, okay? Obviously, this is just a model. This is a representation. Objects on the night sky, if you look at them, they have depth. The moon, although it looks like it's on the night sky, it looks like it's on the same dome, but it's actually closer than everybody else. Everybody else is further away than it. Okay, so there is depth in here that we cannot represent with this model, with the geometry. But we can track them down day in, day out that way. Okay. And we're going to use the Stellarium to see how we can read those numbers. Okay. This is the list of references, explain the motion of the object. Of the objects, they seem to rise from the east and east, from the, where is the east? This way is my east, and fall in the west, okay? And that is because the Earth is moving actually from the west to the east. That's why, that's the spin of the Earth, okay? So let me look at the last unit in here for this week, which is unit 6. Again, this is not a replacement of reading the materials in here. So you guys are supposed to do this reading. Okay, and let me go stop sharing. And we're going to have a summary of this stuff down next week, okay? And don't wait for it. Start reading and get going on it, okay? Share. Unit 6. So in Unit 6, all of this stuff that I was talking about, the night sky and the dome and celestial sphere, of course, that's what you're going to be experiencing with in the activity at the end, okay? With the constellations. As a matter of fact, describe the annual motion of the sun relative to the stars in the horizon. That's exactly what you're going to be doing, okay? Because from the vantage point of view, sitting on the Earth, it looks like the sun is moving, and it's moving on the same line called the ecliptic. And that's exactly what you're going to see. And you will see the stars in the background sitting still. They don't change, except the sun basically moves around them, and all of the other planets do too. Okay, recall the dates and names when the sun reaches its extremum. Of course, one of the things you're going to be talking about on this unit is the summer and the winter solstices, and also the spring and the fall equinoxes, which is one of them is supposed to happen in about a month from today. The fall equinox, okay, around September 20th. So those are the dates that you guys are going to be focused on. Of course, the ecliptic and the zodiac signs, that's part of the stuff that you're going to be looking at in this chapter. And that's exactly what the activity is. You're going to track the sun going around all of the signs of the zodiac and explain how and why the solar heating varies during the year. That is, of course, has to do with the tilt of the axis of the rotation of the Earth versus that of the actual plane of the ecliptic. And that gives me the different seasons, okay? Describe the Earth's precession, because the Earth right now is pointing, or at least the magnetic north is pointing toward Polaris. That actually that moves in around 23 or 26,000 years from that location back to that location. So it's a cyclic operation. At some point, the North Pole will be pointing not toward Polaris, but toward another star in the northern sky, of course, toward Vega, and it's going to come back and so on and so forth. So again, this is the stuff that you're going to be covering in this chapter. So enjoy the reading. If you have any questions, or you don't have, or there is something related to it, please let me know. Again, as I promised, next week we will have a recording of the summary of this three units, but it's really your reading that is going to help you through this thing. Even if we're doing this class live, by the way, even if we are person to person, it's still my interpretation of this unit, and you're still responsible for the reading. And that's why I would still require the book in there. So it's not like this is an exception because it's an online class, you're going to do this reading. It's always true. Okay, the reading is always part of my classes. So if you don't do it, you will have difficulty with the assignments and the class start and everything else. Okay. So this is not an exception just because it's an online thing. So here is the second prompt of the day. Let me go back into the units and let me share again the screen. It's a simple one, actually. All I want to do is to see is, did you do this activity and how did it go? That's all. Stellarium constellations. It went well, or I had difficulty with this and that. Or for example, the shortcuts were not working. And if the shortcuts were not working, of course, what are the replacements for them? There is actually the mouse clicks that you should be able to do. It's the same thing. You can pause the animation, you can accelerate it, you can put the time, and you can actually change the location by double clicking on the object. And you can do a lot of things just basically by doing the same thing as the shortcuts, okay? And how did it go? Were you able to answer all of the questions? Did you have difficulty with one of the questions or something like that? And it could be part of the discussion. As long as it's not personal stuff, you should be able to post it in there. Now, if there is something that really personally you need help with, please let me know and send a private message directly through the inbox, okay? The purpose of this one, again, is to get you to really do this too, to make sure that you have an in-depth understanding of these 2 units more, okay? And also get to know Stellarium up front and up close and in person. And hopefully you enjoy that too. That's actually another objective, okay? So this is so far. Down the road, you will have assignments actually in here, either homework assignments or quizzes and things like that. Other than that, this is the skeleton for all of the weeks. Are we clear on the first 2 prompts today?
I believe I understand it.
Very good, very good, very good. Thank you. I have somebody else also reacting on.
I've been download. I went to that, to the site, that constellation you're talking about right now. I'm gonna go right after class, and I'm gonna see if I can go ahead and download it. I have a computer from IBC, but I've been able to download everything, so that's what I will go ahead. So I at least will let you know that I've been listening, and I'm confirming that's you. It's been very interesting in learning about this. I'm looking forward to your class.
Thank you very much, Koba. Okay, everybody, please take care of these things, and hopefully I've seen also some of the chat comments in here. So I'm glad you guys are following, and make sure you take care of this 2 prompts. So the first prompt has to do with basically the fact that you were able to install it, or you were able to do the web version, and that you're starting to feel comfortable with it and everything looks fine. The second prompt has to do with this activity that I mentioned, the last one, the Stellarium constellations, and whether or not you actually did that. Obviously, if you still have difficulty with the first one, you're going to say that the second one is on hold, okay? The second prompt, basically, I'm still on hold on that because I'm having difficulty with the first prompt. That's fine, okay? These are not supposed to be challenging questions. These are not supposed to be something that you'll have to go and research them. It's part of the class, part of the things you do anyway. So it's not, yes, that's exactly what I was saying, okay? The first one, you're going to tell me what you did. Were you able to install it and install it successfully, or doing the web and you're comfortable with it? And the second one, so the second item of the discussion, you're going to tell me if you did actually or plan to do the Stellarium constellations. Make sense? Very good, very good. So those are so far 2 of them, which brings me to the final and the last type of assignments that we're going to be doing in this class, okay? And it's a big one. So let me go back into, at this point, I will ask you guys to grab a piece of paper and a pen. here's my pen. Okay. And let me share with you the screen to show you that I actually have a piece of paper also. This is my piece of paper. Does everybody see this number in here? Can everybody see my screen, shared screen?
Yes, I can see it.
Very good. So at this point, everybody, I assume, has that piece of paper, a pen, and preferably the book if you have it ready. If you don't have it ready, I'm going to tell you exactly the assignments that we're going to be doing, okay? The problem we're going to be doing, okay? So I have the book with me. So these three things needs to be handy at this point, okay? So I'm going to assume that you have them already. So I'm going to pick up the book and I'm going, this is the 5th edition, by the way, and I didn't see, as I was saying, difference between it and the 6th edition, which is here. I have both of them, okay? So both of them look similar. The 6th edition has some, the picture looks different from the outside, but at least up to this point, there is a difference. There is a difference, I will pinpoint it, okay? So, I'm going to open the 5th edition, and hopefully you guys were going to do too. And we're going to go to Unit 1, page 8, okay? So I'm going to go to page 8 in the book. Okay? And I'm going to look at problem 11. There will be immediately a prompt following this one in here that I need you to guys also submit a discussion item to it. So it's very important to to stay here, okay? So that we can do this one. And at this point, I'm going to do problem 11. So I'm going to read it for those who don't have the book yet. And we're going to write stuff as I'm reading it, okay? So this tells you about the level of math that we will be doing homework on. And immediately before you're basically worried about it, I will tell you exactly how to do this thing. So I really don't want you to be wasting too much time on this thing. So I really want you to do it. Because without numbers, we don't understand a lot of things we do in science. Numbers tells you far more about something than all the words, a lot of the words that you can use. So we really have to get a sense of these numbers. We really have to get an idea of how numbers talk to us. Okay, so problem 11. What would be the circumference and diameter? And in between parentheses, they wrote circumference is equal to pi. And pi, if you're worried about it, it's just another number. It's 3.14. That's what pi is. Just a short for that number, okay? Actually, it still has more digits, but who cares? We only care about the main things. 3.14 times diameter. So I'm expected that you guys are writing these things at this point. Okay, you're following with me, okay? So that's what the book has written for us in between parentheses. So let me continue reading. What would be the circumference and diameter of a ball that would represent the moon if Earth were a volleyball? I don't have a volleyball, but I have a soccer ball. So if the Earth were a soccer ball, what would be the moon? I mean, you need to put something in here in the moon, so that next to it, so that you will have an idea of how that looks like. So that's problem 11. What kind of a ball or object matches this size? So let's do that. In previous question before it, if you use a volleyball as a model of Earth, so I'm looking at problem 10, how big would the 1 kilometer be? The volleyball has a circumference of 68 centimeters. So they gave us, in the previous question, the circumference of the volleyball. Okay, so we know the circumference of the volleyball. The circumference of the volleyball, they said, is 68 centimeters. And this is Earth. Okay, so the Earth, we reduced it in size to become 68 centimeters. This is 30 centimeters. Twice as much as this is about this much, okay? Add to it 68, so this is basically the circumference not the diameter, the circumference. And the circumference, so that we're clear on the concept, this is a beat up ball because we played with it this weekend. So we play with it all the time. So you start from this point and you go around and you go around and you come back on the same point again. So that is the circumference. So if I open this one this way, it's going to be 68 centimeters, slightly over half a meter. Okay. So that is basically what that means. I want to know the diameter, and I want to know the diameter, and the diameter of the ball is actually, if I puncture it from one side and come from the other side, this distance is the diameter from end to end. Okay, twice the radius. That's what the diameter is. So this is pi times the diameter. If I divide both sides by pi, pi cancels from this side, and then here it stays. So the diameter, which is twice the radius basically, would be simply 68 centimeters divided by 3.14. I already did this calculation, and if you don't trust me, put it on your calculator. It's going to be 21 point something. I'm going to rough it up, around 22 centimeters. If you don't trust me, take this ruler and put it across like this and look at the reading, okay? It's about this number, about 22 centimeters, okay? So that's basically roughly how much the diameter is. So the soccer ball, this ball, at least the one I have, is good enough for that purpose. So this is the Earth. Obviously, we know the Earth radius is 6,400 kilometers, or 6,378 kilometers, roughly about 6,400. Twice that much is going to be 12,800. So the Earth diameter is actually not 22 centimeters, although it's going to be a tiny planet, is actually 12,800 kilometers. So this is a model. So this is not real, the Earth. This is a model. So we scaled the Earth down to become like a ball. So this is the concept of scaling. So if the Earth was scaled to be like a volleyball, how big would the moon be? Well, if you look at the units, if you go back into unit 1, the units, the radius of the moon, or the diameter of the moon, is the quarter that of the Earth. So in this model, the moon will be a quarter of this number then. So the moon diameter for the moon must be equal to 22 centimeters divided by 4. And that, if you do the calculation, about 5.5 centimeters. 5.5 centimeters is about this apple. Okay, so that is the diameter that I need to bring with. So here is then how the picture emerges. If this were Earth, this is how the moon would look like next to it. Okay, so this is how the moon would look like next to it. So this is how the model works. As a matter of fact, if you look at it from this vantage point, this is how much the moon covers. Obviously, the moon is closer to you. That's why it looks bigger. But this is how much it is. The shadow of the moon during a lunar eclipse will be that region that is covered only. Not the entire Earth will experience the same lunar eclipse. Okay, only that shadow. And as the Earth rotates, different regions of it will have. Obviously, it doesn't go like this. It goes depending on the year. Okay, because the Earth is tilted a little bit. So this is question 10, question 11, I'm sorry, the type of math that you'll be involved with. So here is the prompt of the day, the third one, okay? When you're given homework assignments like this one, what you're expected to do is the following. Work in teams. You cannot work by yourself. Working in teams is actually a skill that you need to develop in this class. So I expect you to get in touch. You remember that activity, the flat Earth assignment? That was supposed to introduce you to your classmates so that you get to know them and work with them, okay? So get in touch with a few people. You don't try not to make it too large, okay? After 4 people, after 5 people, it becomes too large, and you will be lost in the team, and you wouldn't know what the other 2 people are doing. Try to keep it under 3 or 4, okay? Try to keep it around that 3 or 4 number, okay? Find a team, people that work with you. You can meet online using Discord or whatever you want to use, and work together on these problems, okay? If you have to meet in person, you have to observe the guidelines of the health and safety requirements, okay? Now, conditions are the following. You have to put your own weight. You have to pull your own weight in the team. You have to do things. You cannot rely on other people doing everything and you just copy it, because at that point, that defeats the purpose. You really are supposed to do these things, because the numbers, as you can see from the model, tell things. So you need to work with people. Now, also, research the topic. This is not an exam. This is a homework. It's supposed to teach you things. You're supposed to learn things from it. You can reach out to me before, during, and after, and I will help you. It's not like I'm testing you. No, actually, you're supposed to do these things. And the purpose is that you do these things, okay? And you submit your assignment clean and neat. You may submit it like everybody in your team, or you may defer with them. You may not agree with them, okay? So the prompt of the third prompt of the day is, you can work together in teams, observing the health and safety guidelines, and also contributing to the team, and seeking help wherever resource that you might find. You can Google things, you can text me, send me a message, and things like that, that we're having difficulty with this part. Can we see some insights on how to do it? The purpose is so that you do the assignment at the end of the day. Does this make sense to you guys?
Yes, it does.
Okay, very good. So it's a key thing in here to work in teams. It's a skill that you need to develop, so that when you are in a workplace, the reason why science is actually a collaborative endeavor, people, you will hardly see a person doing something by him or herself. You will find, especially nowadays, publications, you will see so many names. Actually, there is probably half a page just of names working on. And that is the skill that you need to develop. If you go in the workplace also, you're supposed to work with your peers on projects or stuff like that. So it's not like you're supposed to do everything on your own. So that's a skill you're going to take from this class to the workplace, and also to wherever you are, if you're going to do a research or some stuff has to do with science or wherever you are. So you need to develop that. You need to reach out to your classmates, and you need to work together, and try to keep the number basically controlled, so that you actually benefit from the team. And if you need help, reach out before, during, and after, so that we can, if need be, we can go actually on Zoom meeting, and we can go through it. If it's something that I think benefits everybody else, all the other classmates, then I will record the thing. When I will ask your permission to record it, we'll record it and post it for everybody to see that, hey, there was an interesting question, and here is the answer to it, so that everybody else who may have had the same situation, here is the answer to it. Okay, so that is really how I want to say this from this point on. This is, I promise, the last type of work that you will be doing in classroom. I mean, the kind of work, not the only work that you'll be doing. This is the other type of work that you'll be expected to do in this classroom. Okay, so that's the prompt. You're going to put it in your own words. And that is the format for how to handle homework problems. And that is to work in teams, observing the guidelines, and looking for resources and seeking help whenever you need it. Because the point is, you have to do these things. Good? I know at least Stella and Kova agreed. Okay, very good. Also, everybody else. Okay, good. So let's do one more. Okay, gonna look at Unit 2, page 16 now. Problem 10. We're page 16, problem 10. So let me see if I can share the screen again. Share. And I'm going to change color. And I'm going to grab the pen. No, it's still not. Still the same color, actually. For some reason, it went down. Here's blue. Okay, so we're on page 16 now, doing problem 10. Okay. So it says, if the Milky Way were the size of a nickel, I happen to have a nickel in here. And it says between parentheses about 2 centimeters. If you put the nickel on the ruler, you will see is actually about 2 centimeters, okay, in diameter. Okay, so it's true, okay? So we have the nickel. So the Milky Way is a nickel. So this is the Milky Way, which is a big galaxy, hundreds of billions of stars, just like our own sun. Okay, so this is the Milky Way. It says, how big would the local group be? For that, you will have to look at table 2.1. And I know I made a big fuss when I was doing the recording about table 2.1, which is an important table. So in its page 14, if you look at table 2.1, it says the actual size of the Milky Way is actually 50,000 light years in radius. So the radius of the Milky Way is actually 50,000 light years, which means the diameter of the Milky Way is 2 times the radius. And 2 times 50,000 is 100,000. So the diameter of the Milky Way is 100,000. This is represented by a nickel whose diameter is actually 2 centimeters. So that is the Milky Way, 100,000 light years, which is about 2 centimeters in size. Okay, the question is, how big is the local group? The local group is, according to the table, the local group is the size of 1.5 million light years in radius. So this is the radius r. So I need to make it into a diameter. So the diameter is 2 times r, twice the radius. So it's going to be 2 times 1.5 is 3 million. So it's 3 million light years. How big that is? Well, the ratio of the local group diameter to that of the Milky Way is 3 million divided by 100,000. So I need a calculator to do that division. So I have 3 million divided by 100,000. There is a neat trick that you learn from algebra that when you divide the powers of 10, you just cancel the zeros in here. So 5 zeros are gone because I have 5 zeros in the bottom. So I left with 3 and 0, which is 30. So it's 30 centimeters in diameter. But this 30 centimeters is, I'm sorry, 30 centimeters, it's 30, I'm sorry, it's not, it's 30 times bigger. So the local group, when I did the ratio, I found it 30 times bigger than the Milky Way. And the Milky Way itself is 2 centimeters. So I have to multiply 30 by 2 centimeters to find that ratio. So this one is going to be 30 times 2 centimeters to find the actual size of the local group, which is 60 centimeters. So if the Milky Way was a nickel, here, by the way, this is 30 centimeters in length, okay? This is 30 centimeters in length. There, 30. So if I want to find the local group, I have to come up with another one similar to it. So this is basically what the local group is. So somewhere in here there is triangle, and somewhere in here there is Andromeda, and there is another about 45 or so, almost 50 galaxies in this group. This is our local group. This is our neighborhood. Okay. So, and it says also for the local supercluster. That's the other part of the question. It has so many parts in here. How big would be the local supercluster? If you look at the table, the local supercluster has a radius of 50 million light years. So the local supercluster is 50 million light years. And this is the radius, by the way. So the diameter of the local supercluster is going to be twice the radius, and twice 50 million is 100 million light years. Compared to that of the galaxy, which is only 100,000 light years across. So that means the ratio of these two is 100 million over 100,000. And if I do the ratio, I have 5 zeros that's going to disappear, and I will be left with 1 with 3 zeros. So the ratio is going to be 100 million divided by 100,000. Cancel the 3 zeros, cancel the 2 zeros, and I will be left with 1, 2, and 3. So the ratio is 1,000 times bigger. Since the Milky Way is only 2 centimeters, and 1,000 times bigger than 2 centimeters, 2,000 actually. 1,000 times 2 centimeters is 2,000 centimeters. Okay? And that is 2 meters. What is it? Did I make the calculation right or not? Yeah, it looks like it. This is correct. 50 times 2, that's 100, and divided by 100,000. 5 zeros are gone, and it will be left with 1,000. So 2,000 centimeters, how many meters that is? I know there is in 1 meter, there is 100 centimeters. So those two are actually represent the meters. So it's actually 20 meters across, which is a big house, the size of a big house. Okay. So that is how big that is how big, if the Milky Way were this nickel, how big our local supercluster is. Then it asks about the visible universe. That's the last part of the question. So the visible universe, not the entire universe, the visible universe, what you can see, its radius is going to be 13.8 or 13,800,000,000 light years in radius, which means across in diameter is twice r, which when you multiply this number is going to be 27,600,000,000 light years. Again, I assume that you have access to a calculator when you do this calculation. So how big is the visible universe compared to the galaxy? So the ratio is going to be a ridiculous number. 276 or 27,600,000,000 divided by 100,000. That's the radius of the galaxy. So this 3 zeros, these 5 zeros are gone with this one and this one. I'll be left with 276,000 times bigger than the Milky Way. Remember, the Milky Way is 2 centimeters in this model. So I have to multiply this number by 2. So the actual size is going to be for the universe, the visible universe, 276,000 times 2 centimeters. Because this is 276,000 bigger than the Milky Way, and the Milky Way is 2 centimeters. So how much is the actual universe is going to be? The visible universe is going to be this number. So if I multiply the two numbers, first of all, 0, 0, 0, 6 times 2, that's 12. 2 times 7, that's 14 plus 1 that we retain from here, that's 5. 2 times 2, that's 4 plus 1 that we retain, that's 5. So it's going to be 55,000 or 552,000 centimeters. Again, I want to convert it to meters, so 2 zeros are gone. And if I want to convert it to kilometers, 5 zeros are gone. So this is 5.5 kilometers. which is the size of a city, El Centro. So imagine with me that we go to the bank and get as many nickels as we can and sprinkle them throughout El Centro. Okay? And see how much we're going to have in terms of that's how the galaxies are. So if there are 100 billion galaxies, and there are probably more than that in the universe, we have to go to the bank and ask for 100 billion. 100 billion. This is 100. This is 100 billion, by the way. Nickels. They represent the galaxies. And a nickel is basically 5 cents, or 5 divided by $100. So cancel this two zeros. And basically we have to go to the bank and grab $5 billion in nickels. Okay? And sprinkle it throughout El Centro. That would be a fun experiment, wouldn't it? Yes. Get 100 or $5 billion in nickels and sprinkle it throughout the city to do this experiment, to do this model. You guys agree? It's fun? Okay, I agree. Okay. Yeah. Okay. So the last part in here that we're going to do today, the last example. I'm just giving you this example. Hopefully you guys have a flavor of what these numbers talk to you, what they say, okay? And also to understand how to do these things. It's going to be page 24 from the book, and we're going to do question number 9. Okay. Question number 9 from the book says the following. The radius of the sun is 7 times 10 to the power 5. So this is the radius of the sun, kilometers. So our sun, the radius of the sun. Okay, kind of lazy. I don't want to write the whole thing. Radius, I just wrote R in there. And you will see that common actually in when we do problems, like we use symbols a lot. Okay, it's just symbols. They don't mean anything. I mean, they mean what they represent. That's all, radius. Okay, and that of the Earth is, so the radius of the Earth is 6.4 times 10 to the power 3 kilometers. Okay. Show that the sun's radius is approximately 100 times that of the radius of the Earth. Okay. When we're doing questions like this ones, we have to be very careful. We're comparing one to the other. And in order for me to compare one to the other, I'm going to do the ratio and see how big they are, okay? For doing the ratio, and we have units in here, we have to make sure that the units are the same units. Because if they are not, we have to convert. We cannot compare apples to oranges. We can compare only apples to apples and oranges to oranges. That's the key thing in here. Since both of them are in kilometer, then I can cancel them, so we're safe in here, okay? That's one thing. The other thing, after I deal with the units, then the next step is to deal with the powers. It's more important to focus on the power than these numbers first, okay? So I have 10 to the power 5, and I have 10 to the power 3 in this ratio. When I'm doing a ratio like this one, I first write the base, which is 10. Then I'm going to talk about the exponent. The exponent, if it's in a numerator, keeps its sign. So if it's positive, it stays positive, because in here I'm assuming it's positive, that's all. So it stays positive. If it's in the denominator, then in this case it changes sign. That's all. If it's positive, it has to become negative. If it were negative, then it's going to be positive. That is the rule on how to do the ratio of exponents. So I can do 5 minus 3, that's 2, 10 to the power 2. And 10 to the power 2 is just basically another way of saying 10 times 10. That's what 10 to the power 2 means, which is 100. So this ratio here is 100. Okay? Now I have to deal with this ratio, the last one after I deal with the units and then the powers. I have to deal with the rest of the part of the scientific notation in here, which is the ratio of 7 divided by 6.4. Well, if I put it on a calculator, 7 divided by 6.4, that is equal to 1.09, some change in here. Okay, this is actually negligible. I'm going to say roughly it's about 1, because it's 1 plus some change. Okay, 1 plus some negligible number in here. That is really not relevant. So the answer is going to be then, this is roughly 1, not exactly, but roughly 1. I have 1 times 100 and the units cancel. So it's about 100 times. So the sun is about 100 times more in diameter or in radius than the Earth. In terms of volume, it's actually about 1,000,000 times bigger. Because the volume, you have to multiply the radius times the radius times the radius 3 times. So I have to multiply this ratio 3 times, 100 times 100 times 100, it's 1,000,000 times. So again, to go back into my model now, if this is where the sun, I need to pull, remember, this is about 22 centimeters in diameter. So I have to divide 22 centimeters in diameter by 100. So divided by 10, it's going to be 2.2 centimeters. If I divide further 2.2 centimeters by 10, it's going to be 0.22 centimeters or 2 millimeters. So I need to pull an object that has the same size. I have here this structure in here that I use for all kinds of things. So I'm going to pull from it something of that size. Okay. Actually, this is probably too big. I don't know if you can see it or not. Let me share with you. Let me stop sharing the screen so that you see it here. So this is the object in here. And if you put it on the meter stick, it's actually more than 2 centimeters. So I really have to divide this 2 millimeters. I really have to divide this by half. Okay. This is a good substance. It has actually magnetic properties. I bought it from the laboratory in Chicago, and we went to visit there. Visit Fermilab. It's a nuclear accelerator. We took this. I went with the students there. Okay, this is roughly about 2 millimeters. Okay, on the ruler in here. So I'm going to see how the Earth would look in front of the sun. Let me pick up a place that is not too dark. It looks like it's a dirt now. So this is how the Earth would look roughly compared to the sun. Okay, it's an interesting aspect of this. Okay, looks like it's negligible, isn't it? It's about 1 million of this can fit inside the volume. Okay, let me put it back to where I got it from. Numbers tell you the story. That's why this is important. Numbers speak and tell you how really things are. And sometimes it actually helps to model things, because sometimes numbers themselves actually, yes, you have the powers and everything else, but when you put them into a physical presentation, then they become really, really in perspective. Then you can see them. That's the purpose of this part. Again, it's not all of you, every week you will have assignments like this one, but when you do, you are supposed to take care according to the prescription. First of all, put your team, work together on these things, make sure there is a consensus. If you don't agree with them, that's fine. Look for help, look for resources, and submit it to the best of your abilities. This is the answers to the questions asked. Okay, so that's the third prompt of today. Any questions?
That's good, thank you.
Very good. So I know we have a big deal also. Let me remind you of it. Actually, I sent you messages yesterday, 2 or 3 of messages. So I just want to remind you about this assignment. It's important assignment because it serves for me for two things. First of all, it has a big weight, it has 20 points. And then also it helps me basically submit the attendance for the college because we are required to report the attendance based on the census data, for the census data. So they are required to do that. So please make sure you do that. Please don't spend too much time researching the topic. It's more about you than the actual topic. It's for you to introduce yourself to your classmates so that they get to know you, and then also to react to other people so that you know them. And among other things is this assignments that you have to work with them anyway, and to have a communication way of communicating with them. The deadline for the first part is this Thursday. The deadline for the second part is this Saturday. And if you have difficulty with these things, please let me know. There were a couple of students, and I don't know if it's in this class or another class, that they said for some reason this unit is locked. If you have the same situation, please reach out to me so that we can meet and fix this problem, because it's not locked. I know a lot of you submitted this assignment, so I know it's not locked. You may be running into a situation where you have a cached value. Sometimes basically the browsers, instead of displaying the actual page as it looks like right now, they give you a history of it and how it looked like probably 2 weeks ago or something. For that, we really need to clear the cache or do something to fix the problem, okay? So that is basically what I've learned so far. And unless you guys have a request for this Thursday to meet, I'm going to see you guys on Tuesday. I will be available again Thursday during the same session, and we can record it. Actually, the Thursday session, if we meet, well, it's going to be recorded, okay? It's only the office hours and the private meetings that may or may not be recorded depending on the topic. That's good. So let me stop the recording.